I thought it'd be cool to look at Fourier transformations today. I know the concept may seem a little bit confusing in class, but hopefully this demonstration will make it more clear. So to start, a Fourier transformation simply means that any complex waveform can be broken down into simple pure tone sine waves. So I thought it would be cool to take a complex waveform like the bell from class and break it down into sine waves, which sound like this. So let's look at the frequency spectrum of the bell. So as we can see here, it seems that there are pure tones around C7, F8, and F9. C7 is around 2000 Hz, F8 seems like it's about 5000 Hz, and so on. In order to model this waveform, all we really have to do is put pure tones at these specific points, and then change the attack and decay, meaning shape the waveform so it gets loud at the same point that the bell gets loud. So let's do that now. So here's the first iteration of our Fourier transformation. As you can see, it doesn't really sound much like a bell. But if we look at the frequency spectrum, it has a fundamental right at C7. So essentially what I did is I put a pure tone right at that note and then modeled the attack and decay so that it sounds somewhat like a bell. But I think we can do a lot better than this. So here's our second iteration. I hope you guys feel like it sounds a little bit closer. So all I did here was add a second note at the next resonant frequency that we saw in the first EQ of the bell. So that's around F8 right there. So as you'll notice, there are also some frequencies above as well. And to quickly explain those, no synthesizer is perfect. So even though I've put pure tones right at these 2 points, there's still some noise up above. And all I did was kind of accentuate that noise so it looks a little closer to the original EQ. So here's our third and final iteration. So again, I just added F9 there, which was resonant in the original bell recording as well. If we just listen to them side by side. So obviously it isn't perfect, they don't sound exactly alike. But that's only with 3 notes put in. Imagine if I were to add 10 or 20 or 100. That's what the concept of a Fourier transformation is. As I continue to add notes, as I continue to add pure waves, I can approximate complex waveforms. To quickly connect this with in-class concepts, each of your inner hair cells is associated with a specific frequency range, or a given pure tone. You can imagine that if you were to sum up all of the relative activations of each of your inner hair cells, you would essentially have enough information for a Fourier transformation, in that you have pure tones activated at specific levels over time. That's exactly what our brain does in processing auditory information. It essentially performs a Fourier transformation of complex waveforms using our inner hair cells.